Every single day, millions of us step into a little metal box and just trust that it's going to carry us, sometimes dozens of stories, straight up into the air. We hit a button, we feel that little hum, and then we arrive. But behind that incredibly smooth, seamless experience is this remarkable feat of engineering designed to handle forces we don't even think about. Today, we're going to pull back that curtain on the single most critical component that you've probably never, ever noticed.
So really think about it for a second. It's not just the motor that's pulling you up, or even the big steel cables holding all that weight. What is the one system that keeps that car perfectly aligned, absorbs all the little sideways jolts, and, this is the most important part, acts on the ultimate final failsafe in a crisis?
Well, the answer is right there, running the entire height of the shaft, completely hidden from view. They're the guide rails. You can think of them as the silent steel spine of the entire elevator system. And as this analysis from Novin Pooya Elevators shows us, they are the true unsung heroes of our everyday vertical travels. Okay, let's really dive into this. A guide rail is not just some simple piece of track. It's this high-precision steel beam that's doing two massive jobs at once. First, it's providing a perfectly straight, smooth path for the elevator car and the counterweight. But second, and this is absolutely crucial, it's the surface that the emergency brake has to clamp onto to stop the car dead in a worst-case scenario. So it's got to be perfectly smooth for the daily ride, but also unbelievably strong for that one moment you hope never ever comes. All right, so let's talk about the guide rail's day job. Every single trip, whether you're going from the ground floor to the second floor or all the way to the penthouse, puts these rails under a constant, complex barrage of forces. It is so much more than just keeping things straight. We can basically break down these everyday forces into two main categories. First up, you've got your static loads. This is just the simple, constant weight of everything just hanging there. The car, you, all the other passengers, and that massive counterweight. But the second the elevator starts to move, you introduce what are called normal dynamic loads. All the forces of starting up, slowing down, and even tiny little movements. I mean, just think about all the different forces that are at play on just one trip. The rails aren't just supporting the simple up and down weight. No, they're constantly fighting inertia when the car starts and stops. They have to absorb these tiny side-to-side vibrations to make sure the ride feels smooth. And they're even engineered to handle an unbalanced car. Like when everyone for some reason crowds into one corner, the rails have to deal with that too. But look, managing a smooth daily ride, that's just the beginning. The real genius, the true art of guide rail engineering, isn't about handling what's normal. It's about being prepared for the absolute abnormal. This is the core principle of safety engineering, and it's something Novin Pooya Elevators analysis really hammers home. You don't just hope for the best, you meticulously, painstakingly plan for the absolute worst. Every single calculation is made with the assumption that something somewhere could go catastrophically wrong. So, to do that, engineers analyze four critical scenarios, what they call load cases. First, you have normal operation, which we've covered. Then there's something called a buffer impact. That's if the car were to overshoot the bottom floor. In some places, they even have to design for a seismic event, like an earthquake. But that fourth case, well, that is the single most violent test that the entire system is built to survive. And this brings us to the climax of our story, the emergency stop. We are talking about the moment the safety gear activates at full speed. Just try to imagine this, the entire weight of a fully loaded elevator car, moving fast, being brought to a sudden, violent stop. All of that kinetic energy, all of that momentum, it all has to be absorbed and dissipated almost instantly by the safety gear clamping down with just incredible force right onto the guide rails. Now, to understand just how massive this force is, engineers use a concept they call the impact factor. It's basically a multiplier that tells you how much bigger the force of a sudden stop is compared to just the simple static weight of the car. Think of it like this. It's the difference between just holding a bowling ball in your hand and trying to catch one that's been dropped from a roof. So what does that multiplier actually look like? Well, during an emergency stop, the forces don't just double. Engineers have to calculate for an impact factor of anywhere from 2 all the way up to 8. Yeah, just let that sink in for a second. The force that the guide rails have to withstand, without bending, without breaking, without buckling, is suddenly up to 8 times the weight of a fully loaded car. That is an absolutely astronomical amount of stress, and it's all concentrated right on those 2 steel beams. So the big question is, how is that even possible?
And this brings us to the blueprint, the engineering that makes this incredible feat of safety possible. It's a systematic process of analysis and calculation designed to guarantee that the rail will not fail.
The answer lies in a super meticulous structural analysis that checks for every single possible way the rail could fail under that immense load. It's a methodical process that leaves absolutely nothing to chance. So, engineers perform 3 critical checks. First, a bending analysis, which asks, will the rail bend or flex too much under the sideways force? Then, shear analysis. Will the force literally slice through the steel, especially near the support brackets? And maybe most critically, buckling resistance. This determines if the massive downward compressive force will cause the entire rail to crumple and collapse, kind of like an aluminum can that you step on. And this whole process is incredibly systematic. You see, the engineers, they input all the key data: the car's weight, its top speed, the exact steel profile of the rail, even how far apart the support brackets are. Then they run all the calculations for bending, shear, and buckling, and each and every one has to pass a strict safety check. If anything fails, anything at all, the design gets stronger. Maybe a thicker rail, maybe closer brackets, and then they run the whole test all over again until it passes. Now, this is really important. This isn't just one company's internal process or a good idea. These calculations are mandated by strict international safety standards, things like EN 81 in Europe and ASMEA 17.1 over in North America. These global rules make sure that no matter where you are in the world, the elevator you step into is built to the exact same, incredibly high, non-negotiable standard of safety. So what does all this complex engineering and all these intense calculations mean for us? The people actually riding in the elevator every day. Well, it means we can ride with absolute confidence. The Novin Pooya elevator analysis that really inspired this whole explainer puts it perfectly. It describes the guide rail calculations as forming the vertebral column of safety, ride comfort, and long-term stability. And that's just the ideal metaphor, isn't it? It's a system that's strong, it's supportive, and it's absolutely essential. At the end of the day, it's this hidden, rigorous engineering that transforms what could be a really precarious journey into one of the safest forms of transportation on the entire planet. It's the reason our daily ride is so smooth, so stable, and so, well, forgettably reliable. So I'll just leave you with this thought. The next time those elevator doors slide shut and you start to go up, will you take just a second to think about that unseen steel spine diligently and silently having your back?